The morning of February 10th, 1943, dawned pale and cold over Akron, Ohio. A fine dusting of snow lay over the smokestacks and rail sidings that stretched toward the Cuyahoga River. Inside the Firestone laboratories, the air smelled faintly of alcohol and sulfur. A man in his 40s, narrow-faced and bespectacled, leaned over a set of glass beakers arranged like an alchemist's altar. His name was Dr. Robert McKenzie, a chemist once considered brilliant but impractical. On that morning, he was attempting something every expert in the rubber industry had quietly deemed impossible: to create a tire compound that could survive the stress of mechanized war without a drop of natural rubber. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Outside his laboratory window, the war had already begun to consume the world's supply of rubber. Since the fall of Singapore, the previous February, Japan controlled 90% of global production. The plantations of Malaya, Sumatra, and Borneo, once the arteries of Allied mobility, were now sealed behind enemy lines. Every jeep, truck, and bomber tire in the American arsenal suddenly represented a vanishing resource. Washington's calculations were grim. At the current rate of consumption, the U.S. military would exhaust its rubber reserves within a year. That morning, McKenzie dipped a glass rod into a viscous, translucent syrup, a strange hybrid polymer he'd produced through the experimental copolymerization of butadiene, and a compound so obscure that even his colleagues doubted its potential. He pressed the rod between his fingers. It bent slightly, then returned to shape. "It shouldn't do that," his assistant muttered. McKenzie smiled faintly. "Exactly," he said. In that instant, though no one in that quiet laboratory could have known it, McKenzie's impossible rubber would become one of the unsung materials that kept more than 50,000 military vehicles moving through the mud and blood of North Africa, Italy, and France. His work would never earn headlines, nor would his name appear beside generals or presidents. But his formula would embody the quiet genius of wartime innovation, a chemistry of survival born not from abundance, but from desperate scarcity. Across the Atlantic, the Wehrmacht strategists had made their own calculations. German rubber supplies had already begun to fail under the strain of mechanized war. Horses replaced trucks, tanks were immobilized for want of tires. Field commanders wrote increasingly bitter reports about material paralysis. Yet even the most pessimistic German analysts believed the Americans were doomed to follow the same path. Without the plantations, one German industrial officer noted in late 1942, the Americans will be forced to fight a static war. Their vehicles will die where they stand. It was a reasonable assumption. Rubber, unlike steel, could not be mined, forged, or captured. It grew from trees fragile, living organisms that required tropical rain and years of cultivation. When the Japanese closed the Pacific sea lanes, the Allies were effectively cut off from nature itself. But in the laboratories of Akron, Baton Rouge, and Louisville, nature's monopoly was quietly collapsing. The man at the center of this story, McKenzie, had been recruited from the Goodyear Tire and Rubber Company in the late 1930s to work on what was then a fringe idea: the artificial creation of long-chain polymers capable of mimicking natural rubber's elasticity. His colleagues, steeped in the cautious conservatism of industrial chemistry, regarded it as a kind of scientific vanity project. Synthetic rubber had existed for decades in small quantities, but it was brittle, temperature-sensitive, and economically absurd. Germany's own chemical titan, IG Farben, had spent the better part of the 1930s perfecting a version known as Buna S, short for butadiene styrene. It worked barely. The Reich's automotive and military industries depended on it by necessity rather than preference. German engineers joked that Buna tires die faster than their drivers. What McKenzie proposed in 1941 seemed reckless: a reformulation that substituted a petroleum-derived monomer for styrene and added trace stabilizers that had never been tested at industrial scale. He argued that this could create a rubber that not only mimicked natural latex, but resisted heat and abrasion far better. His superiors dismissed it as theoretical until the fall of Singapore transformed theory into existential urgency. By the spring of 1942, President Roosevelt's Rubber Reserve Company had summoned every major tire manufacturer to Washington. The order was blunt: cooperate or perish. Competing corporations were commanded to share patents, research, and technical staff. Trade secrets were erased in a single meeting. McKenzie found himself reassigned to a joint team of Firestone, Goodyear, and Standard Oil chemists, tasked with producing a war-grade synthetic rubber within 6 months. It was an impossible deadline. They had neither the equipment nor the feedstocks, but they had something the German chemists never did: freedom to improvise. Inside the Firestone lab, McKenzie began experimenting with catalysts that conventional industrial wisdom considered unstable. He used sodium metal suspended in alcohol to trigger polymerization at low temperatures, creating an unusually uniform molecular structure. The result was a material that, when vulcanized, retained its elasticity even at freezing temperatures and resisted cracking under heavy loads. In field terms, it meant a truck could drive 3,000 miles before needing replacement tires, more than double the performance of early synthetic compounds. While McKenzie's work unfolded in quiet obscurity, the global drama around him intensified. The U.S. Army was mobilizing faster than any industrial force in history. Hundreds of thousands of vehicles required millions of tires, hoses, seals, and gaskets. Rubber became not merely a resource but the bloodstream of modern war. A single medium tank required more than 800 pounds of it. Every B-24 bomber consumed over 1,000. Without rubber, engines leaked, brakes failed, and aircraft caught fire from unsealed fuel lines. To meet the crisis, the government authorized construction of 51 synthetic rubber plants across the continental United States. But even as these vast facilities rose, their output remained uncertain. Many early batches of synthetic rubber failed catastrophically, turning hard under cold or disintegrating in heat. The Army reported tires peeling apart on test tracks in Louisiana and truck convoys stranded in the Arizona desert with melted treads. By late 1942, production schedules were slipping behind military demand. Inside Firestone's laboratory, McKenzie worked 16-hour days, scribbling equations on chalkboards until his fingers cramped. His assistant later recalled that he often muttered the same phrase: "It has to move if it can't move. Men die." In November of that year, his persistence paid off. A small experimental batch labeled Formula R17 completed a 1,000-mile durability test with negligible wear. The results astonished military inspectors. Within weeks, the compound was approved for scaled production under the generic code name GRS for government rubber, styrene. Though McKenzie's variant contained less styrene than any other formulation. His signature adjustment, the inclusion of trace copolymers derived from butanediol, gave the material its unusual toughness and flexibility. By January 1943, GRS, based on McKenzie's variant, was being poured by the ton into mixing mills across the Midwest. In a nation starved of natural latex, this new synthetic flowed like salvation. Tires, gaskets, waterproof boots, even aircraft fuel bladders were produced from it. By the time American forces landed in Tunisia that spring, tens of thousands of vehicles rolled on McKenzie's creation. On the battlefield, no one knew his name. They simply knew the trucks kept moving. In North Africa, where heat exceeded 120 degrees Fahrenheit by midday, German and Italian supply columns faltered as their tires shredded on burning sand. American convoys using the first GRS tires endured the same terrain for weeks without major failures. Reports from the U.S. Army service forces noted a near 50% reduction in tire wastage compared to previous shipments. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. A German staff officer captured in May 1943 wrote incredulously in his diary, "Their trucks do not stop. Even in this heat, the rubber lives." The irony was complete. The same German chemical tradition that had pioneered synthetic rubber had been surpassed by the nation it sought to defeat. And the man who made it possible was a soft-spoken chemist from Akron, whose greatest triumph would remain buried in technical manuals and production reports. Yet the story was larger than one man. McKenzie's breakthrough represented a philosophical divergence between two warring systems of thought, the authoritarian precision of the German industrial state and the chaotic cooperation of American democracy. The Germans centralized control in IG Farben, restricting experimentation to preserve hierarchy. The Americans abolished hierarchy altogether, allowing rival companies to merge knowledge in a collective act of technological improvisation. Where Germany relied on command, America relied on trust, and that trust, multiplied across laboratories and factories, produced miracles. As 1943 unfolded, McKenzie's compound was quietly refined, its viscosity and cure times adjusted for mass production. By autumn, total U.S. synthetic rubber output surpassed 300,000 tons annually, more than twice Germany's peak wartime capacity. But behind the numbers lay a human truth. Each successful batch of McKenzie's formula meant another convoy supplied, another battalion transported, another wounded soldier evacuated from the front. To the men who drove those trucks, the tires beneath them were just rubber. To McKenzie, they were the boundary between movement and paralysis, between life and attrition. In a letter to his wife dated December 12, 1943, he wrote simply, "They don't know it, but they are rolling on my mistakes." By the opening months of 1944, the American home front had become an organism sustained by chemistry. In every industrial city, the rhythmic thunder of mixers and extruders marked the heartbeat of a nation in motion. Each new synthetic rubber bale that left the factories of Akron, Baton Rouge, or Port Neches carried within it the quiet logic of McKenzie's discovery, the ability to keep mechanical motion alive in a world otherwise deprived of nature's gifts. The war's supply arithmetic was brutal. The United States Army, Navy, and Air Forces together consumed more than 800,000 tons of rubber annually. A single armored division required over 40 tons just for its vehicles, spare parts, and personal gear. The entire Allied effort depended upon the seamless conversion of crude oil, grain alcohol, and industrial waste gases into elastic material. Every truck that left a depot in Tunisia, every jeep that climbed the rocky slopes of Sicily, every bomber that took off from English airfields for the continent all owed its movement to a material that, 3 years earlier, had scarcely existed outside the laboratory. Inside the Office of War Production, the reports that crossed General Lucius Clay's desk told a story both astonishing and precarious. Synthetic rubber output had reached 400,000 tons by mid-year, but the feedstocks butadiene and styrene required constant coordination with petroleum refineries and chemical distilleries. A delay in one refinery could stall an entire tire plant. The system had to operate like a vast circulatory network, each artery precisely timed. To many German analysts after the war, it seemed inconceivable that a democracy, with its overlapping jurisdictions and political debates, could maintain such synchronized precision. Yet it did. For McKenzie, the war's second half became a paradoxical mixture of triumph and anxiety. His Formula R17, now standardized as GRS Type 1500, performed far beyond expectations. Field tests from North Africa to New Guinea confirmed its resilience. Tires retained elasticity under both desert heat and monsoon humidity. Reports from the Army's Motor Transport Service in late 1943 recorded an average tread life of 10,000 miles, a figure once deemed fantasy. The War Department's internal bulletins quietly celebrated the practical end of the rubber crisis. Yet McKenzie felt little satisfaction. Each success demanded another iteration. A compound resistant to aviation fuel for self-sealing tanks, a gasket formula that would not crack at 40 degrees below zero in Alaskan convoys, an insulation coating for electrical systems aboard amphibious landing craft. Every new application revealed the same principal motion depended on molecules. While the United States surged ahead chemically, Germany's synthetic rubber effort collapsed under its own architecture. IG Farben's Buna works at Schkopau and Hulls suffered repeated bombings in 1944. Their processes, already burdened by scarcity of catalysts and skilled labor, degraded under the weight of bureaucracy. Even before the bombings, Farben's chemists had struggled to control polymerization yields above 70%. Without natural latex to blend, German tires grew brittle, cracking in the cold of the Eastern Front. General Guderian complained bitterly that our tanks die of exhaustion, not battle. The contrast was most visible to the German prisoners who found themselves shipped to the United States after the North African and Sicilian campaigns. At Camp Clinton, Camp Shelby, and Camp Polk, these men watched endless convoys of American supply trucks roll by each on 6 fresh tires. To them, the abundance seemed magical. Few realized that the apparent miracle was the result of polymer chains forming invisibly in reactors half a continent away, built upon McKenzie's and his colleagues' equations scribbled in chalk only 2 years earlier. In April 1944, the War Production Board requested that McKenzie join a small delegation visiting several army depots to assess long-term tire performance. At one such facility near Fort Benning, Georgia, he stood beneath the blistering sun as mechanics inspected worn treads from trucks that had returned from Italy. The tires bore gouges, bullet scars, and shrapnel holes crudely patched with vulcanized plugs, yet most had not failed. A quartermaster captain handed McKenzie one of the battered casings. 2,000 miles through the Apennines, he said. Still holds pressure. McKenzie turned the heavy circle of black rubber in his hands. It's not elegant chemistry, he murmured. Just stubborn chemistry. That night he recorded in his notebook a reflection seldom found in technical journals. We measure success in tons, but each ton means motion. Motion means survival. Across the ocean, the same principle defined: defeat. German supply officers calculated tire allocations by the kilometre. Panzer divisions received replacements in single digits. Many resorted to grinding down worn treads and layering them with salvaged soles from soldiers' boots. An entire mechanized culture that had once defined modern war was reverting to the horse. When Allied forces landed in Normandy in June 1944, McKenzie's compound played an invisible but decisive role. Every amphibious truck, every jeep rolling off the landing craft, every landing gear tire of the C-47 aircraft towing gliders, all were made of GRS. The logistical miracle of D-Day rested on a molecular backbone engineered in Akron. The German High Command, analyzing reports from the field, could not comprehend the scale. In Berlin, an intelligence officer remarked in disbelief, "They drive as if tires grow from their soil." He was closer to the truth than he knew. In a sense, the tires did grow from American soil, from corn converted into ethanol, from petroleum drawn from Texas and refined into butadiene, from grain alcohol turned into styrene. Nature had been recreated in the image of industry. By autumn of that year, American synthetic rubber production surpassed 700,000 tons annually. The cumulative output of all German Buna facilities, even at peak efficiency, never exceeded 1/6 of that amount. For the first time in history, an industrial society had transcended natural resource limitations purely through chemistry. But Mackenzie's own world narrowed. The relentless pace of war production took its toll. Letters to his wife grew shorter. "The days smell of benzene," he wrote in August 1944, "and the nights are full of equations." He refused offers of promotion, insisting on remaining close to the laboratory benches. To colleagues, he seemed weary, but his focus never wavered. In October, he supervised a new series of experiments introducing carbon black reinforcements to extend tread life by nearly 50%, an innovation later credited to the collaborative work of multiple firms, though Mackenzie's notes contain the earliest complete formulation. Meanwhile, the human consequences of this chemistry played out far from the laboratory. In the Ardennes that winter, American convoys delivered ammunition and fuel over snow-covered roads. Temperatures plunged below zero, yet GRS tires remained pliant, where natural rubber would have stiffened and cracked. German tanks, advancing on patched tires and steel rims, found themselves immobilized in icy ditches. Logistics determined destiny once again. By the time spring reached Europe in 1945, the war was effectively decided. The synthetic rubber program had produced more than 2 million tons since Pearl Harbor, a figure that defied every pre-war prediction. McKenzie's impossible formula, refined through countless adjustments, accounted for nearly one-third of total output. In Washington, officials spoke of him only in passing, one of the early chemists who made the thing workable. He neither sought nor received medals. When victory came that May, he was back in his laboratory, cleaning glassware. A colleague recalled asking him how it felt to have won the war with rubber. McKenzie smiled thinly. "Wars are never won," he replied. "They just stop running." After the surrender, as Germany lay in ruins, American occupation authorities invited surviving Farben chemists to inspect U.S. synthetic rubber facilities. Among them was Dr. Wilhelm Krauss, once head of polymer research at the Hulls plant. At a tour of the Port Neches complex in Texas, he stared in disbelief at reactors 10 stories tall, feeding continuous flow polymerization lines. He murmured, "We thought it was impossible at this scale." An American engineer responded quietly, "So did we, until we stopped competing with each other." The irony was profound. The chemical weapon of victory was not secrecy but openness, an industrial ecosystem where rivals had shared everything for survival. In July 1945, McKenzie attended a final conference of the Rubber Reserve Company in Washington. He presented data showing that GRS tires manufactured with his modified catalyst had maintained 85% elasticity after 3 years of service. The figures would later underpin the civilian rubber standards of the post-war automotive boom. Yet when asked what the achievement meant, he answered only, "It means we can move again without fear." The end of hostilities brought no parade for chemists. McKenzie returned to private life, declining offers from industry to patent his formula. "It belongs to everyone who drove on it," he told a reporter years later. He died in 1958, his contributions largely obscured by the collective anonymity of wartime research. But the molecules endured. The same polymer backbone that kept 50,000 wartime vehicles rolling became the foundation of modern tire production, medical equipment, and countless industrial goods. Synthetic rubber now constitutes roughly 70% of global rubber consumption, a direct descendant of those desperate wartime experiments. In the decades that followed, historians of technology would look back at the synthetic rubber program as one of the most decisive industrial mobilizations in human history. Yet within that vast machinery, the story of McKenzie remains singular, a quiet man confronting the limits of nature and proving that intellect could substitute for geography. To the German officers who once believed control and hierarchy guaranteed efficiency, the synthetic rubber program revealed a deeper truth. In an authoritarian system, knowledge serves power. In a free system, power serves knowledge. One produced obedience, the other invention. Long after the last tank had rusted into the soil of Europe, the vehicles of peace trucks carrying grain instead of ammunition, buses instead of troop transports still rolled upon his chemistry. And somewhere, in the faint hum of tires on an American highway, lingered the echo of that February morning in 1943, when a single chemist pressed his thumb against a translucent film and felt it spring back to shape soft, resilient, and, against all odds, alive. In the first years after the war, America's factories exhaled the last breath of wartime urgency and inhaled the quieter rhythm of prosperity. The same machines that once mixed polymers for military convoys now poured their strength into the tires of civilian automobiles that glittered under peacetime sunlight. Gasoline was cheap, highways stretched like ribbons of renewal, and the word synthetic no longer implied fraud, it meant freedom from scarcity. For the chemists who had lived those years of urgency, the transition felt disorienting. They had spent 4 years measuring time not in minutes or months, but in reactions completed, compounds stabilized, shortages avoided. Now their equations served commerce instead of survival. The Rubber Reserve Company dissolved, its laboratories folded back into private firms. Government records were sealed. Much of the technical correspondence disappeared into archives. McKenzie returned to Akron, carrying with him a small box of notebooks and the weariness of a man who had seen civilization hinge on a polymer chain. He took a teaching position at a small technical college, preferring the company of students to the politics of corporations. When asked about his wartime work, he would shrug. It was chemistry under pressure, he'd say. The molecules behaved better than the men. In those post-war classrooms, he began to speak not of formulas but of philosophy, the moral responsibility of invention. During war, he told his students, we build to survive. Afterward, we must remember why we wanted to survive. His lectures drifted between polymer chemistry and reflections on human adaptability. He compared molecular cross-linking to social cooperation. The strength of a chain lies not in the individual bonds, but in the freedom of each to move a little before it snaps. His students never forgot that line. Meanwhile, the legacy of his work grew silently across the globe. Synthetic rubber plants, once government-owned, passed into the hands of major corporations. Production climbed beyond imagination, 1 million tons a year by 1950, 2 million by 1960. Tires grew quieter, longer lasting. The automobile became not merely a convenience, but a birthright of modern life. Every mile of post-war highway echoed the same molecular rhythm first discovered in that wartime lab. Historians later called it the chemical emancipation, humanity freed from the geographic tyranny of natural materials. No longer bound to plantations in Asia, the world's mobility now sprang from reactors of steel and glass. Yet for McKenzie, emancipation carried its own unease. He saw in the rise of synthetic abundance a faint echo of wartime urgency, the same acceleration, now without crisis to justify it. The machines kept running because they could, not because they must. In a letter to a colleague in 1952, he wrote, "We are now producing peace the way we produced war at industrial scale, without pause to ask what it's for." He was not bitter, only wary. His experience had shown him that invention, once unchained, rarely sleeps. The synthetic revolution expanded into plastics, fibers, coatings, each a distant cousin of the wartime rubber that had carried armies across continents. Society had entered the age of the polymer, yet few remembered that its genesis had been born of fear, not plenty. In Germany, the remnants of IG Farben were broken into separate companies. Former chemists from Schkopau and Hüls, now, working for Western firms, studied American GRS technology with reverence. Many acknowledged privately that the Americans' advantage had not been scientific skill but administrative freedom, the ability to fail publicly, correct collectively, and share discoveries instantly. "You conquered us with collaboration," one German chemist admitted during a 1951 symposium. "We had genius, you had trust." McKenzie never attended those conferences. He preferred his modest laboratory, where he and his students experimented with new catalysts that used less energy. His hands trembled now, his eyesight fading, but his curiosity never dimmed. In one surviving notebook dated 1957, he wrote, "The true miracle is not that rubber can be made without trees, but that men can learn without war." That same year, the Interstate Highway Act was signed into law. As bulldozers carved asphalt veins across the continent, synthetic rubber became the literal foundation of America's new identity, the road-bound civilization. Every tire rolling westward toward California, every child pressing their face against a car window to watch the world fly by, rode upon molecules first forged for survival. McKenzie lived long enough to see that transformation. He once stood at the edge of a new freeway overpass near Akron, watching cars hum past in endless procession. To the bystanders, he looked like an ordinary man admiring the view. Only he knew he was hearing, within the low drone of tires on pavement, the faint whisper of wartime laboratories and the voices of men who had mixed polymers with shaking hands while the world burned. He died quietly in his sleep the following winter. His estate was small, a few notebooks, a collection of glass stirring rods, and a faded photograph of a tire testing track labelled R17 Trial, 1942. No monument marked his name. But the true memorial was everywhere in motion itself. Decades later, when historians began to reconstruct the hidden architecture of wartime science, McKenzie's notebooks resurfaced in a university archive. A young researcher leafing through the fragile pages found a final entry written in faint graphite. "If I have learned anything, it is that scarcity sharpens not only invention but imagination. The first teaches us how to survive. The second teaches us why we should." That sentence would later appear engraved on a plaque outside a modern polymer research center, dedicated not just to the chemistry of materials, but to the ethics of making them. Beneath it, the curator added a single line of commentary. "In every age, the measure of a civilization is not how much it consumes of nature, but how gracefully it replaces what nature denies." And so the story of Dr. Robert McKenzie, the quiet chemist whose impossible formula kept 50,000 vehicles rolling without natural supplies, passes beyond war into the larger memory of human persistence. His rubber no longer belongs to armies or industries. It belongs to the idea that intelligence itself can become a renewable resource, the one material that never runs out. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.